Hi, my name is Daniel Condurache. I'm professor of Iasi Technical University of Iași, Romania. My paper is the state transport and transition matrix in the general Keplerian orbital motion. Introduction. Relative orbital motion is a conceptual frequency present in current and prospective space motion. Main underlying problem is Keplerian motion. Its relative Keplerian motion is modeled by a strongly nonlinear differential equation. Concept for solution and representation theorem given by Condurache and Martinez. An infinite solution of Keplerian motion possible with the help of universal Martin function or with the help of hypercomplex special algebra. Geometrical insights, the Keplerian motion in velocity space take place in a space of constant Riemannian curvature. For example, for elliptical orbit, the space are positive constant curvature. For parabolic orbit, zero curvature, and for hyperbolic orbit, negative curvature. The structure of the paper, a closed form solution of Kepler problem by using hypercomplex algebra, overview and the general z cosine and sine function in space of constant curvature, vectorial regularization and infinite solution of Kepler problem, constant Riemannian curvature in the velocity space, and explicit parametrization of geodesic in velocity space. 2. The relative motion, representation theorem and closed form solution. It's presented the solution as independent of the nature of Keplerian trajectory, open or closed, and on obtain the tensorial constant of motion. 3. A state transition-like operator, similarly to Lagrange coefficient. And 4, the classic state transition matrix revisit, new results and infinite expression. Now use the classical orbital element and making use of general Z trigonometric function. This is a classical Kepler problem and its first integrals. And by a Sudman change of variable, the Kepler problem is equivalent by linear differential equation in variable tau. On obtained by kappa the curvature of Riemannian manifold and define the set of hypercomplex number by this form. This relation is satisfied, and the set of hypercomplex vectors. For elliptical motion, one obtain the hyperbolic number. For parabolic trajectory, one obtain the dual number. And for hyperbolic trajectory, one obtain the complex number. This algebra unify the three cases of motion in Keplerian case. On define the exponential of hypercomplex number, one obtain the cosine and sine function in the space of constant curvature. On define the hypercomplex state vector and hypercomplex radial state but time on fiction time tau. This is the real part, and this is the imaginary part of state vector, and introduce a hypercomplex eccentric anomaly, but this relation, and obtain this result. The Kepler problems is equivalent by this first order differential equation, and this is the closed form solution, and obtained by imaginary part of Iasi, the law of motion of Keplerian motion, and a real part of this hypercomplex state vector, and obtain the velocity of Keplerian motion, and also the radial state R dot. A very interesting observation. This formula work for any case, elliptical, parabolic, hyperbolic, or rectilinear. This is the general Z Kepler equation, and I obtain two very interesting constant of motion and hypercomplex one. This is the expression of velocity in constant Riemannian curvature space. This is the relation of metric that is Riemannian space, and the velocity of curve tangents as geodesic, defined is a tangent model in configuration space. The functions cosine and sine are related to the measure of angle with this Riemannian manifold. Relative orbital motion, representation theorem. This is the initial value problem for relative orbital motion in local vertical, local horizontal reference frame. And this is the expression of closed form solution. RD is the solution is the Kepler classical problem. But this observation obtain a tensor invariant expression for relative orbital motion for non-linear relative orbital motion. It's expressed by this equation is the six-dimensional constant of motion. This is a state of attraction center by rapport of local vertical, local horizontal reference frame, and matrix lambda is which is 4. The propagation of the deputy orbit in local vertical or local horizontal frame is meant by this equation. This is interesting generalization of Lagrange coefficient in this case. On obtain also the straight transition matrix, then this form, and on denote the matrix EM by this expression. On obtain a very compact form, the matrix for state transition. This is the Lagrange coefficient, and this is the expression of this Lagrange coefficient. In conclusion, the hypercomplex algebra was used for infinite closed form solution to the Kepler problems. The generalized trigonometric function cosine and sine offer a natural parametrization of the velocity space for a Riemannian metric in constant curvature. The general solution of relative motion is presented without any assumption of the inertial trajectory of the two spacecraft, chief and deputy spacecraft. A closed four-state transport matrix is presented for relative motion in local vertical, local horizontal frame. And the state transition matrix for relative motion can be determined by using only simply geometrical manipulation. The future work investigate a full hypercomplex approach to the constant curvature network in the metric in the velocity space. Thank you.